So I'm going to go ahead and actually, I'm not going to continue a game. I'm going to start a new game. I've decided in, the course of 24 hours that we should actually focus on um, getting to the content of, like the whole point of what I want to do. And so I want to try to use like this as, a vehicle to discuss like engineering principles and how you would go about determining if you were tasked with designing a thing, how would you go about it? What are some of the steps? And I'm taking my inspiration from Scott Manley. I love his videos. Um, the way that he uses Kerbal Space Program to talk about, space and physics and everything rocketry. And, I just find that amazing. But I want to try to get into the nuts and bolts of some of it a little bit more in terms of like the mechanical structures and the entire systems and actually building stuff in real life. So I want to take it one step further. And so I want to focus on, we started yesterday. I mentioned a light armor block, and I actually shot a little video of me in Autodesk Inventor putting together a large armor block, a large light armor block. And so today I'm going to focus on, let's just look at the mechanics of a light armor block, a small light armor block. And yeah, so we're going to start Lone Survivor. We're going to be creative, offline, and advanced. We're just going to turn everything up so that I can do stuff really super fast. Actually, I don't know what that one means. Adjust inventory size of the blocks. Well, I'm going to turn everything up. Environment hostility safe because I don't want to infinite. Okay, fine. Sure. I only really need 10 kilometers to do this. So that should be, as long as we can pack in enough asteroids to get everything that we need. We'll go unlimited. Okay. Okay. We'll start here. Genius 1% inspiration. Inspiration and 99% perspiration. I mean, that's true. You got to work. 1% inspiration. I don't know how much, when it comes to the creative flow, you just have to kind of empty your mind and you get inspired from time to time, um, from some external something or other. But really, when it comes down to it, your job is to fulfill some need, and so your inspiration comes from the problem statement. So, we got our gravity generator, we've got our nuclear reactor, cargo container. So I want to take a look at these things, these actual, and let's build them. Let's build these bad boys. Some of it will be easier than others. Don't know that I'll be able to pull off a nuclear reactor. I'm good, but I'm not that good. I don't even know if I'm really good, to be honest. Maybe we collectively as YouTube can build a nuclear reactor. That'd be pretty cool. It'd be awesome to bring everybody together in space engineers. So, all right. Let's focus on, because there's so many possibilities here what I want to talk about, but let's focus on the light armor block. Okay, so first of all, let's try to build one. What do I have here in number one? So that's a large light armor block, and here's all the iterations of it. And I think if I hit it again, I can move to a small light armor block. And so I'm just going to put that bad boy right there. So here's my light armor block. Now the way these things work is you can obviously use them to build stuff and things. And so if I stack them together, they automatically like grab on and you get some random shapes, surface texture here to make it interesting for the game. And you can see the seams go away, right? So once you join two blocks together, the seams disappear and it floats off in space. So let's look at the design principles behind a small armor block, small light armor block. And oh man, in creative mode you don't build stuff up, but maybe I can tear it down. So do I have a grinder in my inventory? I do. How do I edit my toolbar? G. And I want character weapon, character tools rather. I'm going to put my welder down here, my grinder down here, and I'm not going to worry about the drill for now. So I got a grinder, so let's see if I can just tap this thing. There, that's what I wanted to show. So you see the basic structure of the light armor block in its various build stages. It shows you the framework. Wow, this really sucks. I'm going to turn my inertial dampeners off and just go with it. Yeah, so now we're floating along at roughly the same velocity. And I'm just tapping my keys here to try to match my velocity vector. So let's look at the structure of this block, and we are actually going to mimic this in real life. So you can see here that we've got several vertical members. I say vertical only because that's the way I'm looking at it now. I really don't have any orientation. But you can see that it's called a space frame. That's the name of that structure. And so what we're going to do is build a space frame in real life. And it's called a space frame because it takes up space, not because it's built in space. And it uses a series of joints and structural members there to give it its rigidity. And it's an effective way to use a material to cover large distances, but also to handle large forces. So some might ask if the space frame is really a necessity in this particular instance. Why not just use a sheet of metal? When you don't have any forces acting on stuff, then you don't need any rigidity. But the tricky part about even though there's no gravity, so these things don't have any weight per se, they do have mass. And whenever you apply an acceleration to a mass, then you get a force. That's F equals ma. That's a law of physics. Okay, so that's F equals ma. I don't remember which one it is. Maybe I should. Maybe I should do a little bit more research on this stuff. But this is all junk that you learn in engineering school. And maybe you forget what it's called, but you understand the basic concepts, and so then you learn how to design stuff using those basic concepts. So what I know is I do need some structure to this thing aside from a flat plate in order to build a structure of a ship, because it's going to undergo acceleration. It's got some mass, it's going to have some inertia, you get it moving, it's going to have some momentum. And so there's law of conservation of mass, law of conservation of momentum, and all these kinds of things that when you look at the dynamics of these structures, doesn't matter where they are, if you apply an acceleration, you're putting force on it. Okay, so if we're going to attach engines to this thing, or if I'm going to bump it around or whatever, then if I just bump around a flat sheet, it's just going to wobble. But if I bump around this rigid structure, then it's going to move as a rigid body. And that's another interesting definition we'll talk about: rigid bodies, non-deformable solids, deformable solids, liquids. We're going to talk about all that kind of stuff. But let's focus on this light armor block, and let's come up with our own problem statement. So, let's say you are employed by some space company, and I don't know who it's going to be. Nowadays there's 100, so take your pick. There's probably only like 6. I don't know. We'll ask Scott about that. But, they want you to build some structure out in space for a space station. So the first thing you have to do is figure out what the design criteria are. What's the functional objectives? What is this thing supposed to do? And you say, well, it's supposed to form the basis of a space station. And so it seems fairly straightforward, but there's all different kinds of space stations. There's all different kinds of questions that have to be answered in order to define the scope of the project. So in this case, is this going to be a life-sustaining space station, or is this going to be just a structure to mount vehicles to that won't have to support life? Is it going to be free floating like this? Is it going to be attached to an asteroid? And so let's go through and we will come up with a list of objectives for this structure. Okay. Project goal. Design a basic structural element to support a space station. All right, there you go. So let's look at different considerations. And I'm not going to use numbers because these aren't in any at the beginning, these are not in any particular order. But of course, that depends on what your client, whether that's your boss, probably your boss. If you're designing a space station, you're probably part of a big organization. Of course, I'm designing a space station and it's just me. So, well, us together. So, you know, these considerations are not in any particular order from the beginning. Let's keep an open mind, use the creative process because engineering design is a very iterative process. And so we'll come up with an answer out of a possible, you know, huge solution field. And these things have all kinds of different definitions. And I'm a big fan of definitions, but I just want to get through some of this. So some of the design considerations for this, you know, these are the specifics. These are what we want to do. So, and these are questions at this point. So clarifications, considerations, questions. I'm going to lump all this stuff in together because these are things. This is just top of the head, you know, quick brainstorming. So, is it airtight? Is it life sustaining? Forces applied. What else do we need? You know, aesthetics. Does it need to look a certain way? How much does it weigh? Oh, is that right? Is that how you spell weigh? I think that's how you spell weigh. You know, mass, material. You know, what else am I missing? You know, rigidity. Is that a concern? Because there's a difference between, and if you're an engineering student or an engineer, you know, there's a difference between, you know, like base functionality for carrying loads and then rigidity design considerations. So if you do apply a load, how much can it move before it fails? So the interesting part of that is it opens up a can of worms. You know, if you have an airtight structure, then you're going to have to design on rigidity because you probably have some seals in there. You know, if they're mechanical seals or if the seals are made by welding junk together, then, you know, maybe that deformation is carried throughout the structure. But if there's elastomeric seals that depend on, you know, some mechanical compression, then you don't want your structures moving away from one another and opening that gap up. And we'll definitely get into elastomeric seals. You know, I'm an agricultural engineer with a specialty in machine design. So you look at hydraulics, like a hydraulic system, very tight tolerances, working non-compressible working fluid for all intents and purposes. And you look at elastomeric seals to provide the zone of influence differentiation of the pressure, right? So you want to retain that pressure on one side, not the other. And in space, there's a pressure gradient, especially if it's a life-sustaining thing. But if you're using any kind of a pressurized fluid, whether it's a gas or a liquid, then you probably want to retain that fluid on one side or the other of some working boundary. So this takes us back to rigidity. We don't want our stuff moving too far apart. Okay. Now, in space engineers, everything is modular. So we know it's going to have to be a modular thing. It's going to have some form factor. So a small light armor block, maybe let's see 1/3 of a meter. How many can fit inside of a large armor block? Let's go back to the game. Let's go back to the game here and just do a little test. So I'm going to come back down to the space station, maybe. We're out here floating. Got my inertial dampeners turned off. See how many small light armor blocks can fit in a large armor block. And I know people have done this before, but since we're here and we're going through it in real life, so there's a large armor block. And I'm going to see if I can't put this thing here. So delete, try to get that in that corner. So there's 1, 2, oops, 3, 5. So a small light armor block is 1/25th of a large light armor block because it's 5 by 5 and 5 this way, right? So what is it? Oops, no, I'm an idiot. What's 25 times 5? So that's engineering right there. Oops, I'm an idiot. And this is kind of a back of the napkin calculation thing we're doing, right? And that's a big concept in engineering, especially during initial phases of design. You don't spend a whole lot of time doing rigorous calculus or matrices or whatever if it comes to FEA or anything like that. You would do a rough back of the napkin calculation. So did my answer just make sense? I went through that in my head. And so, this 25 by 25 square that I've got here, well, I got to bring it out in the third dimension. And I just instantly realized when I said 1/25th, that's totally wrong because I got 25 squared. So anyway, let's multiply 25 by 5 and you get 125. Okay, so a light armor block is 125th of the total volume. We're looking at a volumetric thing here of a large light armor block. So what implications does that have? Does that have... let's not go down that road yet to this thing. And so yesterday I said that a large light armor block was a meter. But now that we're looking at this, let's assume that my person there is, 5'9". Let's just say I'm a male because I'm a male. And I think the U.S. average height for males is like 5'9". Okay, so if we assume that he's 5 feet 9 inches, then our block there is some multiple of that. So let's do some math. I just Alt F4'd out of everything. I'm trying to get all my recording stuff. Engineers like to solve problems. There are no problems. They will create their own problems. Here we are. I'm creating my own problems. I got bored of everyday life, so let's create some problems. So here we are. I'm going to use all the design tools available to me to kind of show you how an engineer thinks. Now there's some perspective here, there's some parallax, and we could figure all that out. But this is a back of the napkin calculation. So